Hello, and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be talking about section 7.1 for Math 1040, the properties of the normal distribution and uniform distribution. Up to this point in Math 1040, what we have been working with, particularly in chapter 6, were discrete random variables. However, here we're going to be talking about continuous random variables. Now, when we were talking about discrete random variables, we were able to find the probabilities of various values relatively simply, because there were only a finite amount of outcomes that were possible. However, here, when we're talking about continuous, we're going to be talking about a range of outcomes that each have an infinite amount of possibilities within those ranges. With that said, that makes it a lot harder to find individual probabilities, and so what we're going to need to do is find a little bit of a different method to find the probability of a range of values here. Now, before we get to that, we have a few definitions. First, the definition of a model. If you ever hear us talking about the word model, what we're referring to is an equation, table, or graph that's used to describe reality. Now, describing reality, we've been working with those really since chapter 2. Anything like a histogram or a two-way table from chapter 4 or the formula for binomial distribution in chapter 6. All of those are things that are used to try to describe something in reality. So model is just a nice word that we use as an umbrella term to take care of anything that we come up with or develop that's trying to describe reality. The type of model that we're going to concern ourselves with here is what we call a probability density function, or PDF. That being an equation that's used to compute probabilities of continuous random variables. No continuous. Those three letters there, PDF, those three letters should look very familiar, particularly since we just covered through chapter 6 recently. In chapter 6, we had worked with binomial distributions, and we had a function called binom PDF that we used in order to find the likelihood of a specific amount of outcomes. Well, PDF. We're going to use that here as well. However, this is going to be used for continuous random variables. So we're going to use this to find a range of values. A couple things about probabilities of PDFs, or properties of PDFs rather. When we graph PDFs, which will look something like a bell curve shape or a nice smooth curve shape, it's supposed to represent all possible values, which means that the entire curve itself should have an area of 1, representing 100% of likelihood. So all possibilities are represented. Also, the height of the graph must be greater than or equal to 0 for all possible values of the random variable. Now, what that means is that when we are graphing this, which as I said, we're typically going to be graphing this like a bell curve shape, we're going to be graphing it so that as I approach either the positive x direction or the negative x direction, the curve itself should be approaching but never actually touching this x-axis. Should get closer and closer but never actually touch it. That implying that even as I go further and further, the values over here aren't necessarily impossible, they're just incredibly unlikely. Also, we want to avoid situations where people would draw a distribution something like this. The problem with this kind of distribution is that it would imply that somewhere over here at this point, we have an instance where we have a value that is actually impossible, that has a value of 0 because the height there is 0. We also run into problems when we go past that intersection point. The area of the curve past that is below the x-axis, which would imply that it has a negative area. Unfortunately, a negative area in probability would indicate that we have a negative probability, which doesn't make sense. All probabilities need to be between 0 and 1. So that's what we're talking about when we say the height of the graph must be greater than or equal to 0 for all values. All right. Now, the first type of probability density function we're going to talk about, or just probability distribution itself, is going to be called the uniform probability distribution. Now, when we say uniform, what we're talking about is the probability here, or the likelihood, the top of this curve. If you notice, looking through this entire curve, it is consistent all the way out, from the beginning, where it's 1 out of 30, to the end, where it's 1 out of 30. Every value in between has the same probability, or more specifically, any range of values. For example, say I have values, let's go from 7 up to, say, 11. Well, in order to find the probability that I get something within that range, what I would do is consider this shape that I've built, and I notice that, well, it has a width, it has a height. This is just a rectangle. Finding the width of this from 7 to 11, that has a width of 4. It's 11 minus 7. And it has a height of 1 out of 30. So then, when I would find this area, let me erase this bad graph over here. When I find the area of that, I'd simply do the height times the width, or length times the width, whatever you'd like to indicate it as. So 1 out of 30 times 4 should give me 4 out of 30. Now that's the probability of that area, because it's just a rectangle. But I could have another rectangle to compare that to over on this side here. Maybe I go from 26 up to 30. So 26 up to the end. And I want to find the probability of that region. Well, that region also has a width of 4. It has the same width. Since it's in a uniform probability, that also means that the height is also going to be consistent. It's also going to be 1 out of 30. So this is also going to have an area of 4 out of 30. So this is what we're talking about when we are referring to a uniform probability distribution. The distribution where any two intervals of equal length, here I had an equal length of 4, these two intervals have the same probability, or they are equally likely. As another example of that, we have on the next page a graph that is a uniform probability distribution function for the distance that a group of toddlers should say, throw a ball. The distance that a group of toddlers can throw a ball. First, we have find the probability from 6 to 9. Well, 6 less than or equal to x less than or equal to 9 really does mean just the values from 6 up to 9 inclusive. So if I draw that here, 6 being roughly there, 9 being roughly there on the graph, and I want to find the area between those values, I see that I have a width of 3, 9 minus 6, and a height of 1/8, giving me a full area of 3/8. Or if I run that in my calculator, 3 divided by 8 is 0.375. Now, I'm going to do a similar process for the second part, which says find the probability of at least 8. So, at least 8. Now, when I'm talking about at least 8, what that means is from 8, which is roughly here on the graph. And when I say at least, what that means is more than 8. Think about it like if I were to invite at least 8 people to a party, that means I should expect to have enough commodities for 8 or more people. So 8 to 10, that has a width of 2 times a height, which is the same as the previous one, is 1/8. So that should give me an area of 2/8, or 2/8 in your calculator should give you 0.25. All right. Now the third part of it is kind of worded strangely the first time you might read it. There's a 25% probability that x is within blank feet from 2 feet. What that means here is that we have the probability given to us, but we don't know how far away from 2 feet I need to go. So the question is, how far do I need to go away from 2 feet so that this shaded region here represents 25% of the data. Well, thankfully, we basically just solved that. We just did 2 times 1/8 equals 0.25. And what we know from uniform distributions is that any interval of equal width will have the same probability. So if a width of 2 resulted in a probability of 0.25, then likewise anything with that same probability would have a width of 2. So if I go 2 feet away from 2 feet, I get an interval with a probability of 0.25. Now thankfully for us, we already solved that, so it was a lot easier to find 2 here. But if we didn't, we could have also solved that using a formula. We know that the width times the length, or the width times the height, should equal the area. So if I know that that final resulting area should be 0.25, and I know that the height is always 1/8 for a uniform probability distribution, then all I need to do is consider what the width of that is going to be, which is my unknown. So I used x for time, so let's say w for width. I can solve for w by multiplying 8 on both sides, thereby removing 1/8 from that left side here. And what I would get is w equals 0.25 times 8. 0.25 times 8 gives you an answer of 2. So there are a couple different ways of solving that. Thankfully, we did already solve the previous one, so that helped us here. All right, so that's a uniform distribution. Relatively simple because more or less you're just finding the area of rectangles. Now, what we're mainly going to be working with moving forward, both in this chapter and in chapter 8, is what we call a normal probability distribution. Now, we tend to use this word rather often. I know in my class I accidentally use that word a lot way before chapter 7 when describing things like bell-shaped curves or symmetric curves, because that's what we eventually start calling them. A normal probability distribution of a continuous random variable whose relative frequency distribution has the shape of a normal curve, otherwise known as a bell-shaped curve. So this right here, this familiar looking shape, or this shape that should look familiar, this is what we call a normal curve. Okay. Now, because this is a familiar shape, something we have dealt with, you likely know a few of these properties already. Since it is bell-shaped or symmetric, what that means is that it is symmetric about the mean. The value in the middle here should be the mean. So it's symmetric and it's centered around that mean. Furthermore, the mean equals the median equals the mode. And what that means is that the curve itself has a single peak at the top here that occurs at the mean, or the median, or the mode. But typically we just say the mean. Now the third one's a little bit different. Likely haven't heard inflection points before. We say inflection points occur at mu minus sigma and mu plus sigma. So one standard deviation down from the mean and one standard deviation up from the mean. Now, inflection points are something that you likely don't hear too much in statistics courses outside of this specific case. Something you hear more in algebraic circumstances. And what it really means is what happens to the slope of the curve as you progress through. So if I imagine I am on this curve and I am in a car or something, and I'm driving up this curve. As I'm going up and up, the slope is getting steeper and steeper and steeper and steeper until I hit that inflection point. Once I hit that inflection point, the slope gets less and less steep as I get to the top of that curve. It's getting shallower and shallower and shallower. So that's what an inflection point is. The point along the curve where the slope changes from becoming steeper and steeper to shallower and shallower. It is also true on this side as well. It's getting steeper and steeper as I approach, and then it gets shallower and shallower and shallower. Think about that next time you go up and down a hill in your car. All right, so those we say happen at mu minus sigma and mu plus sigma. And what that is going to be useful for is that when we draw a curve, so if I were to draw my own normal curve, I'd say, all right, I know the mean is going to be here in the middle, and wherever the inflection points are, that's going to be my indication of where I will put one standard deviation down, and that's where I'll put one standard deviation up. That's where those values should be represented. That way we don't arbitrarily put them too far away or too close to the mean. That way we have a good amount of spacing. All right. Now the fourth point here, the area under the curve is 1. We've already said that before. That was on the first page. That this should represent the full probability, so the area is 1. Since it is symmetric, the area to the right of mu equals the area to the left of mu, and that means that that area is 0.5 or 50%. So if I were to take this curve and cut it right in half, the area on the left side should equal the area on the right side. These should have equal area, and each of those have an area of 0.5 or 50%. And lastly, another note from page 1. As x gets larger and larger or more and more negative, so as I'm approaching the positive or negative infinity on this curve, the graph approaches but never reaches the horizontal axis. So it gets closer and closer to the axis but never actually touches it. All right. Now, because we are working with bell-shaped or symmetric curves, what that means for us is that the empirical rule, or the 68, 95, 99.7 rule, comes back into play. If you recall, the 68, 95, 99.7 rule states that 68% of the data is between one standard deviation down and one standard deviation up from the mean. 95% represents 2 standard deviations away from the mean. And 99.7% represents 3 standard deviations away from the mean. So this is something we had back in chapter 3, so it is coming back. However, it's going to be used in its actual intended purpose as a rule of thumb. Now, what I mean by a rule of thumb is that we're going to use these values, 68, 95, and 99.7, in order to judge the percentages and probabilities that we find to tell if they make sense or not. We're going to use these values as well as the area that would be in their respective tails. For example, 68%, that means that 32% are in the tails, or 16% in each tail. Likewise, for 95, we have that 5% would be in the two tails, divided by 2 is 2.5%. And for 99.7, that means 0.3% are in the tails, divided by 2 is 0.15%, a very small amount are in the tails. We're going to use those three numbers and the area in the tails relatively often in order to judge values that we find to make sure that they make sense. So that's what we mean by a rule of thumb. Always keep these in mind when evaluating, because you want to be able to make sure to see if your values make sense. All right, 2 more things before we get to an example. The effect of the mean and the standard deviation on the normal distribution. Well, if you have a mean of 0, and then you change the mean to a 3, or a higher number or a lower number, and nothing else changes, so the standard deviation stays the same. In this case, the standard deviation stayed at a value of 1. If you keep everything else the same but only change the mean, all that happens is that the distribution moves. It either moves to the right if you increase it, or it moves to the left if you decrease it. The shape of it retains. So the shape of it is the same. However, if you change the standard deviation, from 1 to 2, so if you change the standard deviation in some way, what that's going to influence is the spread of the distribution. So for example here, the standard deviation of 1, this distribution is very thin, and it's centered around 0 and it doesn't spread that far. Whereas this distribution with a standard deviation of 2 spreads much further. It has a lot more room to spread. So remember that mean just influences where the center of the graph is. Standard deviation influences what the spread of the graph looks like. All right. Now a couple examples of these. For these situations, what we're going to do is basically focus on how we would set up these kind of normal distribution problems and how we would knock them down. We'll get to the middle part in 7.2, the part where we find the actual probability. So we'll get to that in a bit. But first, we're just going to talk about how to set it up and knock it all down. So here, we have consider the lifespan of refrigerators are normally distributed with a mean of 14 and a standard deviation of 2.5. What we're first going to do is draw the normal curve and label the horizontal axis. In this case, the curve is already drawn for us, but we just need to label the axis. Now, what we're going to label the axis with are important values from the mean and increasing and decreasing by various values of the standard deviation. So then what I have here is a value right in the middle. That value is a value of 14. That should be my mean. Then I'm going to increase and decrease by values according to the standard deviation. So I see around there, that's probably around my inflection point. That's going to be where my first standard deviation is. So I'll increase by 2.5 to get up to 16.5. Then I'll increase again. 16.5 plus 2.5 gives me 19. And then once more, it gets me up to 21.5. I'm going to do the same thing on the other side. So I'm going to go down 3 instances of the standard deviation. Down 1 standard deviation would give me 11.5, so that's 14 minus 2.5. Minus another 2.5 gives me a value of 9. And another gives me a value of 6.5. This is something we're going to oftentimes do in order to talk about values that are on this curve and try to come up with likely percentages based on values from the empirical rule. So it'll give us a good way to section off pieces of the distribution itself, and we have an idea of how it centers and spreads. So that's how we would do part A. Part B asks, what would happen to the model if the mean were larger? So for example, if the mean went from 14 and it changed into a mean of, say, 20, that would just be a larger value. Well, what would happen here is the center here would change from 14 to 20. So I'd move this center value here over to around there. But that's all that would happen. The shape of it would stay the same. So all that would happen is that the graph would move to the right. However, the shape stays the same. That's all that would happen here if the mean increases. All right. So that's just theoretical, making sure we know what happens with the distribution. For part C, what we're going to do is shade the proportion that's greater than 17 years. So in order to do that, let me see if I can change the color of my pen here. In order to do that, what we're going to do is try to indicate where 17 is on the graph. So 17 is around here. It's a little bit more than 16.5. That's where I'd say 17 is. Now it asks us to shade the proportion that's greater than 17. So what that means is that we want the area above 17 years. So like that. Now, as I said in 7.2, what we're going to talk about is how we find this probability. How we find what this shaded region is going to equal. However, we should kind of have an idea of what that shaded region should be, at least an estimate based on the empirical rule. If I notice, 17 is more than 1 standard deviation away from the mean. Well, if I go 1 standard deviation away, which has 68% in the middle, that means that one standard deviation has 16% in one tail. So 16% in the tail, 68% in the middle. If I notice, this is more than one standard deviation, which means that it is missing that slice right there. Therefore, I expect it to be less than 16%. So I'm expecting something like probably somewhere between 2.5x and 16. That's kind of where I'm expecting my probabilities. I know it should be less than 16% because it's more than one standard deviation away. I know it should be more than 2.5% because it's not quite 2 standard deviations away. So this gives me an idea based on the empirical rule of what value I'm looking for. If I were to find, this really should say P of x, something like that. If I find that the probability of this, say I calculate it and I come out with an answer of approximately like 21%, for example, then I should be able to look at that 21%, look at what my graph says, and say, well, that doesn't seem right. Maybe I plugged something in wrong. I should go back and check. Perhaps I accidentally typed in 15 instead of 17. This is why we keep the empirical rule, so we have an estimate of what kind of probabilities we should be looking for. However, as I said, in 7.2, we'll talk about how to get those probabilities. For now, in part D, they give us that value. They give us that the probability is 0.1151. Now, looking at those values that we estimated earlier, we've estimated it to be between 2.5% and 16%. And 11.51, that is between my estimated range. That is between 2.5% and 16%. So, that seems good. So, we set up the problem, we drew the curve, shaded it, we got the probability here, now we're going to interpret that. First, we can interpret it either as a probability or as a proportion. When we interpret it as a probability, we'd say that the randomly selected refrigerator will last more than, we're looking at 17 years, so will last more than 17 years, we'd say is 11.51%. So when we analyze as a probability, we're looking for a percent. Comparatively, if we analyze as a proportion, what we're looking for is a decimal. So we're going to say here the proportion of refrigerators that last more than 17 years is 0.1151. A couple different ways of interpreting that. So if you see something where it asks you to write it down as a probability, then we're going to write it down as a percentage. If you ask it for a proportion, that means we want it as a decimal. Okay, so that's an example of setting up a situation and analyzing and knocking it down. We have one more of those just to make sure that we know how to do this. Now, I recommend, if you have the lecture notes with you, try this on your own first. So try this page 5 first, pause the video, see how you do, and unpause and watch through to see if you got the right values or not. All right, so here we have Elena conducts an experiment in which she fills up the gas tank on her Toyota 40 times and records the miles per gallon for each fill-up. She determines the mean miles per gallon of her car is 24.6 miles per gallon and a standard deviation of 3.2 miles per gallon. And it first asks us yet again to draw the normal curve and label it. So we know in the middle here should be 24.6. And what we're going to do is increase by my standard deviation 3 times and decrease 3 times. If I increase, I get increasing by 3.2 gives me 27.8. And then another 3.2 gives me 31. And then another one gives me 34.2. If I decrease, I get 21.4. 4 again gives me 18.2, and again gives me a cool 15. So it gives me my values in terms of how it spreads away from the center mean. Then it asks us to shade the proportion between 18 and 21. Again, I'll see if I can do that in another color. And what we're going to do is shade the proportion, try to estimate what kind of area I'd expect from that. All right. Now 18, we have 18.2 as one of our values, and 18 would be just past that. So around there, that's where I'd expect 18 to be. 21, likewise, is just past 21.4. And so we have this area here. Now, we can try to estimate that probability. I noticed that it's, if I go one standard deviation down, I'm taking almost that entire curve, or that entire tail, but I'm missing this bottom section. So what this is similar to is taking the entire bottom tail of one standard deviation away, which is about 16%, taking away the bottom tail of two standard deviations away, which is 2.5%, which means I should expect something around 13.5%. Probably a little bit less because I don't include the full tail here. So I'm expecting a probability that's probably a little bit less than that, but not too far away. And when I see in part C the answer here, the probability being 0.1107, that doesn't shock me too much. Seems about right. Again, if I got something like 3% or 20%, that would seem wrong. Now, if I analyze this as both a probability and a proportion, remember as a probability, that means we're going to be doing this as a percentage. The probability that a randomly selected tank of gas will last between 18 and 21 miles per gallon is, in this case, 11.07%. And as a proportion of times the gas will last between 18 and 21 miles per gallon is 0.1107. So a couple different ways of interpreting that. With that said, that's it for section 7.1. At this point, I recommend going through and trying to complete the homework for chapter 7.1 before continuing on into section 7.2, which will be in a separate video. With that said, I hope this helped, and I wish you a good day.